Oh, sorry about the movie last time. I was recording at 1080p and I've reduced it a little and I think that'll make it not do that anymore. But the movie was just like non-existent last time. So temperature conversions is really all that's left in this numerical, all the numerical problems. And it's probably worth pointing out that virtually all the problem solving we did was just multiplication and division. Did you notice that? A lot of the equations we'll use are like that. The rare exception though is temperature conversions. And just to go through some of these, I will give you these on the test. I'll give you all of this on the test, everything down this page, including this bit. I just copied it straight out of the book. But let me go ahead and write down. Temperature in Fahrenheit is 1.8 times the temperature in Celsius is 32. If you rearrange the algebra, you get this. And then to convert to Kelvin, the equation is temperature in Kelvin, temperature in Celsius. All right, so 3 different temperature scales. Your book doesn't do this, but I have always liked so 9 divided by 5 is exactly 1.8. So this is actually an exact number. It is an obvious when I write it that way. Maybe it's obvious this way, because those are just 2 integers. Those are exact. I've always liked that formula better. But it'll work out correct if you just use 1.8. I would add to this 273.15 is actually the more accurate way to do it. In terms of questions in this book, and I guess on the test, I'll stick to the way, I'll use this number, but just remember that that's exact. And I won't use the 0.15, but that tends to come up in lab if we ever do anything with it in lab. Yeah, way towards the end of the semester, we'll use that for a conversion. But for now, we can just do this. Right, so if I subtract 32 from both sides, and then I divide by 1.8, both sides, that's how you get this one on the right. Yeah, in Kelvin, you could do that too. Temperature in Kelvin minus 273. Temperature in Celsius. So applying this is really just about being careful with the addition subtraction rule. 104 degrees Fahrenheit, convert this to C and K. So we want to use, so we have Fahrenheit, so we want to use this so we can solve for Celsius. Says 4. So now we're mixing addition, subtraction, and multiplication, division in one problem. The way you handle that is you do your subtraction first, and whatever your result of that is, continue. So if I said, and I just plug it into my calculator, I'm gonna get 72. That's correct because this has nothing after the decimal, this has nothing after the decimal, so this has to have nothing after the decimal. If it were 104.3 minus 32.11, then my calculator says 4.3 minus 32.11. But I can't leave it like that. What do I need to do?
Only have one number past the decimal point.
Correct. So your answer would be to there. The 9 rounds to 1 up. 2 is what you would have. But this one's very simple. So 72 up here. With nothing after the decimal, because really it was this that I was solving. All right, so once you've fixed up that number for the correct significant figures, now you do multiplication division rule. 72 divided by 1.8, and remember that's exact. Infinite significant figures, really zeros all the way out. 2 significant figures, so my answer needs to be 2. 72 divided by 1.8. My calculator says 40. Is that good? Is that the answer? It's not. I need to show 2 significant figures there. I'm only showing 1. I have to do this to indicate that 0 is significant. And if you were asked to put it in scientific notation, oh, and of course you're going to want to put degrees Celsius per unit. I think all of these are straightforward enough. Celsius to Kelvin is just this. Now that we've got 40 degrees Celsius, what is that, 313? Do that right. I did that in my head. 13. This is addition, so nothing after the decimal, nothing after the decimal. So 313 is fine, nothing after the decimal. I think y'all are okay with temperature conversions? All right, I won't hang on these, but I did give you some to practice, right? At least from the back of the book. So, a few temperature conversions. I think that rounds out everything I want to do in chapter 1. So that takes us to chapter 2. I suppose I'm covering everything from the start in chapter 2. So much of this, at least the first 4 sections, are just a bunch of semantics. I guess things to memorize, nothing too deep to explain. But if you're new to chemistry, you'll want to hear all of this. Oh. I will give you this on the test, one of these. This is better than the one up here because it's got the names. So take a look at this. Even if you had never taken a chemistry class before, you've heard of the periodic table. I bet you recognize the shape. But the reason the shape is the way it is, but towards the end of this chapter, we'll talk about why we would organize them in the rows that way. But do use this to practice, because it's like a big cheat sheet. There's a lot of stuff there that's kind of given because you get one of these on every test. Is that everybody? I like this periodic table because it's got the actual names of the elements and the symbol, so you don't really have to memorize it. It would help to be a little familiar with it. I mean, because you'll get a question and you have to hunt around for the name. Maybe know some of these up here and these just kind of to help you orient. To quickly be able to look at an atom and realize it's not there, and you're looking for it down here somewhere is helpful. But facts to know. Really, this is just a lot of tedious semantics, but we always teach this in introduction classes. So there's a name for the element, and there's what we call the atomic symbol. If you see a capital B next to a lowercase r, that necessarily means bromine. That is, bromine is over here. So look at your periodic table, you can see the Br, and you can see bromine. There's also a B. If you saw just a capital letter B, that means boron. Somewhere on the periodic table, there's this for carbon. Way down at the bottom in these rows, we will very rarely reference these. There's a U, it stands for uranium. And again, you don't have to memorize these, you'll have that on the test. It's just a matter of not wasting too much time hunting for things. You will also see, but this is an uppercase and a lowercase. That means those two letters go together when we're talking about copper. If you saw Cu in, say, a chemical formula, that means copper and uranium. So the lowercase letter tells you that lowercase letter goes with this uppercase letter. They're taken together as the chemical symbol or whatever. Some of them have 2 letters, some of them have 1. The ones that have 2 letters, the second letter will be lowercase. Like I said, just a bunch of semantics here. Since I'm giving you the periodic table, you don't really have to sit around memorizing things like this. This is just telling you these old world words for some of these things we know of as where the symbol comes from. Like you would think gold would be G or GO, but it's actually AU for the old word. Aurum, old Latin word. All right. Important fact. Now, this isn't on your periodic table, so you have to learn a little bit. The blue ones are called non-metals. So everything over, really everything, if you look at this stair step shape, everything in the top right corner diagonally, that's all non-metals. Hydrogen goes with those. Why we would designate these together won't be obvious until later. All the green ones are called metals, so you have metals and non-metals. These are the metalloids, the tan colored ones here. And sometimes they behave like metals, sometimes they behave like non-metals, so they're called metalloids. A quick way to use your chart, I think this stair step is on there. But if you think of a stair step going all the way down to here, you ignore the two on the bottom, the one on the right is non-metal, TS is part of the metals. And then everywhere else, above and below the stair step, they're all metalloids, except for these, or really it stops here, so it's Al and PO, aluminum and polonium. You ever heard of a dog food called Alpo? That's just a mnemonic. So everything down the stair step are metalloids, except for this one and this one, Alpo. Just a mnemonic to help you remember. So metals and non-metals are kind of central to things we'll do later. More semantics. Going across, a row is called a period. A column is called a group. Groups have similar properties, so chemically, there's something very similar about all of these in this column. True of all of these, there's something similar about all of these, something similar about all of these, something similar about all of these. So that's called a group, that's called a period, rows are called periods, columns are called groups. And so the first period, I know it's a weird shape and there's this big gap here, but the first period is this one and this, hydrogen and helium. The second period is these two and these, so that's all second period. I know there's a gap there, but you just skip the gap, that's all one period. That's the second period. You've got the third period. When the fourth period starts, that's when we start filling in this middle part. The groups have names. There's really two different designation systems. One, you just number from left to right, 1, 2, 3, 4, 5, 6, 7, 8. So this is group 16, this is group 13. They also have this other designation. You've got 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Then you have B, which are all the transition elements, 3B, 4B, 5B. I don't tend to ask questions like, what group is this? But it's good to be familiar with them just because of the questions you'll get. Like, you can get a question like, name a group 14 element that's in period 3. That would be this. And you can look on your periodic table and pinpoint it. Group 14 in period 3, and you look on your periodic table, you see Si, you also see silicon. So metals and non-metals, probably the most important thing. Another important thing here is, if you look at your periodic table, bring mine up here. So we're all looking at the same thing. You've got, for each one of these boxes, it's a different element. Notice they're numbered, like this has a 1, and then that's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's called the atomic number. It's just more semantics, but the atomic number literally means that's the number of protons it has. So atomic number and number of protons are like synonyms. They mean exactly the same thing. I'll say more about protons and electrons in a second. You've got the symbol, you've got the name. This will come up later. That's how much it weighs. A couple other things. This first column is called the alkali metals. The second column is called the alkaline earth metals. These are called the halogens, and these are called the noble gases. So names of 4 different groups. They all have names. For some reason, textbooks love to point those 4 out. But all the groups have names. I think everything I just told you is what's down here. I suppose this is worth knowing. So metals are shiny, they conduct heat and electricity easily. Non-metals are poor conductors of heat and electricity. But the utility in knowing metals versus non-metals, I kind of ignore the metalloids because any given metalloid sometimes behaves like a non-metal, sometimes like a metal, and exactly what that means won't be obvious for a little while. So what exactly is a metal versus a non-metal on a deeper basis we'll get to. Just off the top, I showed you where the metals and non-metals are. So maybe this is a good question. Chlorine, titanium, okay. Chlorine, if I pinpoint it for you, is, here, let's do this, is over here. Is that a metal or a non-metal? It's a non-metal, it's in that top right corner. Titanium is over here. Is that a metal or a non-metal? I left out, here's another piece of semantic knowledge. These two and all of these, excluding this bit in the middle, those are called main group elements, and these are called transition elements, or transition metals, because they're all metals. So just vocabulary, so you understand what you're reading in questions and what I'm saying. So transition metals are on the middle. These at the very bottom are called inner transition metals. I don't tend to ask those questions on a test, but those might show up in the wording of questions, just so you're not lost when they come up. All right. Periods, groups, general stuff. Krypton, this is krypton. The name of this group is the noble gases. All right, so that's all just really stuff that doesn't need to be explained. It's just some facts to know, some facts to memorize. Okay, let's focus on the human body thing. The most common elements, at least on Earth, are these in the upper rows. And nearly all, well, let me see what this next section is so I can, compounds. This is skipping ahead, but I think it's worth mentioning it here. Compounds. Well, that's when, so you have all these elements, they're individual little things. When they come together and stick and make larger things, those are called compounds. Compounds are, there are covalent compounds, there are ionic compounds, metallic compounds. There's one more. Called coordinate covalent. We're not really going to study that one though. I just like to put it there because that's a complete list of all the compounds throughout the entire universe. First, those are the 4. And we don't even really talk much about metallic compounds. These are the 2 main things we focus on: the covalent and the ionic. I won't go here, but And these are very different in what causes them to come together and stick together, these four categories. But covalent compounds are made up only of the nonmetals. H2O, if I drew it, there's an oxygen bonded to two hydrogens. Hydrogen and oxygen are both nonmetals. C2H6, if I drew the molecule, this is what we call the molecular formula. It tells you what atoms are there and how many are there. So 2 carbons and 6 hydrogens. 1 oxygen and 2 hydrogens, so you've got water and what we would call ethane. But notice those are all nonmetals, and I could go on. There's what else can I do? So there's another covalent compound. Kind of a synonym here. What I'm drawing here are molecules. They're necessarily covalent compounds made up of only nonmetals. This one's formula would be C2H7 with 1 nitrogen. For some reason in chemistry, we leave off a 1. We do this in more than one place. You would almost expect there to be a 1 there. For some reason, chemists 200 years ago just decided writing the 1 is pointless. But this means there's 1 nitrogen in this molecule. This means there's 1 oxygen in this molecule. Ionic compounds, can you guess what ionic compounds are? Based on what I put here and what I put here. It's both. Made up of NaCl. 1 sodium atom, 1 chlorine atom. Chlorine is a nonmetal, sodium is a metal. Ionic compounds aren't molecules. They really make up large, orderly arrays that sort of alternate. So you can see that as one sheet that I'm building out larger and larger. And of course, they're 3-dimensional, so I would have a chlorine right here in front of this sodium and another chlorine here in front of this sodium. And then in between them, there would be a chlorine there, and there would be another sodium in front of this chlorine. So I could build it out alternating. So picture a 3-dimensional lattice. And these things are stuck together. This is what an ionic compound is like. So that's an ionic compound. And these are some covalent compounds, aka molecules. The metallic compounds, I won't say a lot about them, but ionic, think minerals, like in this room, ionic compounds. Maybe there's some in gypsum. That's all I can think of. Oh, and the stone. These walls aren't stone, you know, those big brick institutional type things, like in your high school. So those are probably a lot ionic compounds. So think minerals. If you were standing out in the middle of the woods, to find ionic compounds, you probably have to go a few feet in the ground. So rocks and minerals is where we'll find a natural source of ionic compounds. Metallic compounds, they're exactly what you thought a metal was before you came and took a chemistry class. That's metal, this is metal, that's metal, that's metal, you know, metal, coins, stop signs, things that go clang. Okay, those are metals. Everything else is a molecule, covalent compound. Virtually all of your body is made up of molecules. Synthetic fibers are made up of molecules. Non-synthetic fibers are made up of molecules. If you were standing out in the woods where you would point to see the covalent compounds, I said organic compounds. subset of covalent compounds, but nearly everything in the natural world is organic, contains carbon and hydrogen. But you would be looking at trees and plants, air, water, but virtually everything in this room that's not metal and not like gypsum or whatever is going to be covalent compounds. Natural wood, covalent compounds, organic compounds. Plastics, your clothes. So anyway, just as an orientation. I like this, I introduce metals and non-metals. This is how they break down. And truthfully, we started chapter 2, chapter 3, and chapter 4 are like that, and we really don't cover these individually. Metallic compounds come up very rarely, but we're going to spend a lot of time on ionic compounds and a lot of time on covalent compounds. Next 2 chapters. But we're building towards that, talking about atoms, the periodic table, the structure of atoms. So compounds come up a little too early, I think, but they're showing 3 molecules here, 3 covalent compounds. And then they don't say anything about ionic compounds. So I went from semantics on the periodic table, quick introduction to compounds. That's not in your book. I think that belongs in every book, but it's not there. I don't do a lot of this molecular art stuff. It's becoming more and more popular, and I probably should, but you can't even really see that, but there are bonds in between these. You might see these in 1152, but black is carbon, red is oxygen, nitrogen is blue, hydrogen is white. What is this asking? I can't see the bonds there either, but there are bonds in between these carbon atoms. Anyway, let me just go past that, because I won't put those on the test. Okay, structure of an atom. Again, still kind of semantics. We'll talk kind of specifically like this about atoms, and then we'll just kind of move on, and we really only care about electrons later. But, so in the nucleus of any atom is where you find the protons. You also find neutrons in the nucleus of the atom, the very center of the atom. And the electrons are kind of, I'll say nucleus here. The electrons are just kind of floating out here somewhere. The structure of these electrons is something we'll cover before we're done with this chapter. But protons and neutrons are in the nucleus together, and electrons are all out here somewhere. Earlier I said that the atomic number that you see on this periodic table, 1, 2, 3, 4, 5, 6, that's the number of protons in the nucleus. So of the 100 or so atoms, there's a specific type of atom that has only 1 proton in its nucleus. That's in the top left corner of your periodic table. That's what that 1 means, 1 proton. There's also another type of atom that has 2 protons in the nucleus. Top right, helium. Then 3 is lithium, 4 protons in the nucleus. What about neutrons? Well, neutrons are a little weird. Most of the time, I don't want to say that. Generally, there's as many neutrons as there are protons, or there's a good bit less neutrons than there are protons. But don't focus on the neutrons now. They're weird. They don't follow a nice simple pattern. The pattern to pay attention to is the protons and electrons. For a neutral atom, that is a non-ionic atom. Neutral means it has the same number of electrons as it does protons. So for the first one, it has 1 proton in it. That atom naturally has 1 electron floating around the outside. So if you take these literally, there's 1 proton, I'm going to erase the neutron. 1 proton in the center, and that means 1 electron floating around the outside for the neutral atom. Atoms can gain and lose electrons, so I'm waving my hands a little when I say same number of electrons as protons. But for this whole section that it's going through, it sticks with the neutral atom. We'll talk about ions and how can gain and lose electrons. But you never gain and lose protons. It is possible to blow apart a nucleus so the protons and neutrons go flying everywhere, but that's nuclear chemistry, that's a nuclear bomb, that's nuclear energy. It's not really a chemist's domain or a physicist if you're dealing with splitting the atom. This is what they mean by splitting the atom. You blow apart the nucleus, the protons come out. But in chemistry labs and stuff, the protons always stay together as a nucleus. Meaning if I'm in the lab, I'm working with this and it's hydrogen, it's always going to be hydrogen. The number of protons in the center is never going to change. I can make hydrogen react and make water, and I can put it through a chemical reaction and make this molecule with those same hydrogens. They break apart, they reform bonds on the carbon, but always there was just one proton in the nucleus. Things are going on with the electrons if you transition from one to the other, but the protons stay the same. So the atomic number is the number of protons. If I wanted to draw helium, I'll put another proton there. Helium has 2 protons and 2 electrons. If you want lithium, number 3, another proton in the nucleus, another electron, there's lithium. So it's a very simple pattern. So the atomic number literally means the same thing as the number of protons in the nucleus. And in some sense, that's how the periodic table is organized. Just reading from left to right like you do on a page, it goes 1, and then 2, and you go down a line, 3, 4, 5, 6. But why the gaps and all of that is really kind of where we're going. Electrons have a negative charge, protons have a positive charge. So if I have lithium here, I don't know why we don't put plus symbols on the P, because we always put the negative symbol on the electron. If you zoom in real close and you just look right here on this atom, and these electrons are really kind of moving around, you would sort of see a little area of negative charge. If you zoomed in here, you'd see an area of positive charge. But if you kind of zoom back, they're all canceling each other. Meaning this overall atom is not charged, it's not overall plus or overall minus, it's neutral. But if I lost an electron, now this electron is canceling one of these P's, this electron is canceling another one of these P's, but there's no electron canceling the third one, so this overall atom, the way I've got it drawn here, would have a +1 charge on it. This is skipping ahead to ionic stuff, but just to say it while we're here. In this section, we're going to stick with neutral atoms. But if this could gain an extra electron, then this would be an overall negative charge on here. Do you see that, the imbalance between positive and negative? That's how we get ions. But that's skipping ahead again. And lithium doesn't do either of those two things. And the neutron is neutral, and like I said, I just kind of want to ignore it because it doesn't follow a simple pattern. But I'll bring it up again briefly, and then we'll never talk about it again. Nucleus is a dense core, contains protons and neutrons. Electron cloud, okay, that's fine. And maybe I need to say this, but like charges repel each other, and a negative positive charge will be attracted to each other. If you shot 2 positive, let's say protons, towards each other, they start to build up resistance as they got closer, and then they go and miss each other, because there's literally an invisible force that's keeping them away from each other. The closer they get, the stronger that repulsion is. Same with 2 electrons, 2 negatives, they come together, they're gonna go whoosh. But if I just held a positive and a negative in each hand and let go, they're gonna go shh and go towards each other. So like charges repel each other. When the charges are different, they attract. So useful fact when we start talking about ions. All right. Just more semantics. The atomic number, the number of protons, and the letter Z are all synonyms. They just like chemists decided to use Z to represent If you want to write it in the abstract, Z means the atomic number. And for the neutral atom, however many positive charges there are in the nucleus, that's how many electrons there are floating around it. So the rest of this is just kind of the same questions over and over. So they're using a picture here. I probably won't use pictures on the test, but if you're looking at that particular atom, that's supposed to be a blow-up of the nucleus. How many protons, neutrons, and electrons are in the neutral form? Give the atomic number, identify the element. Well, you've got your periodic table. You can count the 2 positive charges. The 2 other colors there, the kind of tan-looking colors, are neutrons. So which element is that? Helium. What you want to do is go 1, 2, 2 positive charges. That's the atomic number, and then you find it on here. It's number 2. You've got He, you've got helium. That's helium. That means it's going to have 2 electrons floating around it. You can see the neutrons there. That's the only reason it's fair to ask how many neutrons, because, like I said, neutrons don't follow a simple formula. Helium happens to have the same number of neutrons as protons, but that's not a strict pattern that continues. So going across here, number of protons, 2. Number of neutrons, 2. You see them there. How many electrons? There's going to be 2. What's the atomic number? It's 2. Identify the element. It's helium, aka He. So as long as you got your periodic table, that should be very easy and obvious. Something called the mass number. That's the number of protons plus the number of neutrons. And that's symbolized with an A. I'm looking here, this A. Okay, I think we're good on the video. Okay, it's still going. So that just adds one little twist to these types of questions. Determine the number of protons and neutrons, give the atomic number and the mass number, identify the element. So can you identify the element? 1, 2, 3, 4, 5, 6 positive charges, so which element is it? It's carbon. You look on your periodic table, you're looking for that 6, it's carbon. You can count these neutrons, 1, 2, 3, 4, 5, 6, 7. So this has 7 neutrons. The atomic number is 6 because it has 6 protons. The mass number is 6 plus 7, which is 13. Identify the element. It will have 6 electrons floating around it because it has 6 protons. So all of these questions are really redundant. What is the mass number of an atom that contains 42 protons, 42 electrons, and 53 neutrons? You would add the neutrons and protons, so 42 plus 53, that gives you the mass number. We do this because the electron is like 1/1000th in mass to a neutron or a proton, and neutrons and protons pretty much weigh the same, very close to the same. So the weight of electrons is negligible, so we call it the mass number because pretty much all the mass comes from the nucleus. And this word isotopes, that just refers to the fact that, like for instance, chlorine has 17 protons, but some chlorine atoms have 37 neutrons, 37 minus 20 neutrons, and some have 18 neutrons. So any sample of chlorine atoms, about half of them have, I gotta do this now. 35. Okay, 35 minus 17 is how many? Is that 18? just can't do math in my head.
Yeah, 15.
Not quick. 35 minus 17. Yay, 18. Okay. So 37 minus 17 is 20, right? This is A, and this is Z. That is mass number, atomic number. That's the number of protons in a chlorine atom. 17, because if it's a chlorine atom, it has 17 protons, period. That never changes. But about half of any sample of chlorine atoms has this many neutrons. The other half of that sample will have 20 neutrons, so they will weigh slightly different from each other. But the weight we use for that is a weighted average of the two, but I'll get to that later. So anyway, one more thing to add to all this semantics about mass number and atomic number and protons is we use the symbol. Well, in general, it's the symbol and A and Z. So there's a superscript up here for the mass number, and then a subscript down here for the atomic number. So these two, you see them symbolized there, is 35. And then there's another type of chlorine atom that's 37 and 17. That's not the number of neutrons. That's the number of neutrons plus protons. If you just subtract 17 from 35, like I did here, so you pretty much have to be given the mass number and the number of protons to find out how many neutrons. It's not a simple pattern like everything else. And there's different, so these are called isotopes, 2 different isotopes of chlorine. Honestly, this is about the end of isotopes, and we won't talk about it anymore. Neutrons are what make this seem confusing. But there's a simple pattern to neutral atoms. 1 proton in the nucleus, 1 electron. 2 protons in the nucleus, 2 electrons. That's true all the way through all the atoms. The atomic number is the number of protons in the nucleus, and it's also the number of electrons in the neutral atom. These are just more of these same types of questions. For each atom, give the following information. The atomic number, that one's 50. The mass number is 118. The number of protons, same thing as atomic number, so that's 50. Number of neutrons, you subtract 50 from 118, it's 68. Number of electrons will also be 50. And you can look that up on the periodic table and find out that that's 10. SN, it is right there, 10. So I won't hang on any more of these because they're all just kind of redundant like that. And I'm going to skip past atomic weight for now. We're going to deal in grams per mole when it gets important. I might come back to this. But let me skip it for now and get to the more nitty-gritty. Group, I covered that. Main group elements, transition, intertransition. Okay, I mentioned all of that earlier. I haven't outlined questions for y'all to answer yet. Okay. Electron structure. I'm going to do this my way. It's very simple. And then I'll come back and show you all this tedious stuff. Books have gone to using a diagram like this. but don't look there. Books I used years ago always did it this way. So picture the nucleus, all right, and let's say it's got a bunch of protons in it, and I've got to put electrons where they go. The first place I'm going to start putting electrons is picture a sphere that's kind of out from the center of the nucleus, a certain distance. I'm going to symbolize that this way. So if you picture a scale here going up, that is distance from the nucleus. I don't know where I get that spelling from. So let's say the nucleus was here. The sphere, what I'm saying is, oh my God, it's nowhere near. So there's the nucleus, here's a sphere, and the radius out from that sphere is what I'm drawing on this line. All right, and now picture another sphere a little further out, a little bit bigger. So its distance is to here. And then I want to do 3 lines for the next one. And maybe they're just a little bit further out. So that's what I'm diagramming when I do this. But to keep it from being too messy, think like this. We're to the point where we're going to talk about what are known as electron configurations. This is how the electrons build in the atoms. Each atom on the periodic table has a specific configuration. And here's how to start one of these. You go 1, 1, 3, 1, 3, 5. 1, 3, 1. You just draw that. Draw it right in front of your face on a piece of paper. Then this is very, very easy. So this is a sphere. This is a sphere. These aren't really spheres. They're, if you have the nucleus, you've got your inner sphere and then the next sphere. Those 3 at the same distance. Instead of a sphere, it's kind of a cigar shape. There's one going this way, one going this way, and one coming straight out at you. That's what the 3 are. The 5, kind of the same idea, at least you can picture it this way, of 3 equivalent cigar-shaped, what we call orbitals. But don't overthink this. This is what you need for all of these types of questions. What is the electron configuration of? Oh, crap, no, so that'd be that with sulfur. All right. Find sulfur, it's on the right side, over here. And what's the atomic number? What is it?
16.
16. You see it? So how many electrons does it have? Neutral atom, 16. This is what you do. 1, 2, 3, 4, 5, 6, 7. Do these individually and then fill them back. 8, 9, 10, 11, 12, 13, 14, 15, 16. That's the electronic configuration of sulfur. I know it's abstract, but that first sphere, if we were talking about hydrogen, it would only have 1 electron period in it. And then if we could magically make another proton appear in the nucleus, so the nucleus had 2, and then we let another electron go into it, it would pair with that first electron. So what I'm showing here is electron pairs. Electrons actually have a little magnetic moment, and you know how magnets have the north and the south. Have you ever played with magnets? Your generation plays with those neodymium magnets. We used to have big bar magnets. You could push them around with each other because they would repel, and you turn them around, they go together. Those neodymium magnets do have a north and a south. You ever tried to Like they stick together real easy, but if you flip one over and hold them to each other, they want to shoot away. So that's what makes them stick together. They have a little bit of magnetism. And that's what this is showing them flip. So you've got north to south, north to south. But anyway, that's overthinking it. All you need to know is 1, 1, 3, 1, 3, 5, and then electrons pair. So when you start adding them, when you count up, you pair them. When you have, even up here, where you have more than one line on the same level, you do them singly first, and then you go back and pair them up. If you stop in the middle of this, it should look like this, 2 by themselves and 2 paired. So when I went across here, I went 1, 2, 3, and I went back here. Well, I guess I was on 16 by then. But. So if you fill them like that, that's the electronic configuration. The rest of this is my favorite word today, semantics. The single ones, you can think sphere, we call those the S-type orbitals. And they're the same. This one's a sphere a little further out. This one's another sphere, bigger, all nested inside each other. These 3 that are kind of elongated along the axes, x-axis, y-axis, z-axis, we call those P. I can't give you any good reasoning why those are called P. It has to do with spectroscopy. S meant singlet, P meant plural, and then they realized there were more. So they should have called this the 1, some Latin word for 1, some Latin word for 3, some Latin word for 5, but this is what they did. D meant diffuse, but that doesn't help anything. But these are D type orbitals. D. Oh, and I haven't said that yet. This sphere is called an orbital. This sphere is called an orbital. Each of these are their own orbitals. 3 orbitals here. Just a word. And then these have numbers. This by itself comprises the first shell. So this is a 1s. This comprises the second shell, so that's 2s. This is the third shell, so that's 3s. These are 2p orbitals. 2p, 2p, 2p. By the time we get to the third level, we have the 1, the 3, and a 5. But these are all 3. And the first D-type orbitals you get is when you get to this third layer. So like I said, this is just semantics. This is just what we call these things. This is one way you can represent the electron configuration of sulfur. I'll write a big S down here so I don't forget which atom I'm on. There's another way you can write this. It's kind of a condensed way. You would go 1s, 2 electrons in it. 2s, 2 electrons in it. 2p has 6 electrons. P orbitals have 6 total. Then you've got 3s, that's 2, and then 3p has 5. That's just another way to represent the electron configuration of sulfur. So if you're not liking this, that's because it's just kind of rote memorization. This is how chemists decided to map this stuff. What your book does, and all books seem to do now, is they stack the S's and they shove the P's over here, and they stack the P's here, and then they shove the D's even further over. I don't find that useful. 1s, 2s, 2p, 3s, 3p. I haven't mentioned this yet, but now is a good time to mention it. Unfortunately, this neat pattern, there are 5 and 7. That's actually the pattern. It just keeps going up with the odd numbers. So the first shell has only this one orbital. The second shell has these 4 orbitals. The third shell has all of these. And the fourth shell, this is 4s, the 4 p's, 4 d's, and these are called f orbitals. But the unfortunate fact is, for one thing, I didn't tell you why this happens. That's way too deep of a question. You just accept that as the base platform of our knowledge here. Unfortunately, the 4s These actually overlap. The 4s actually comes in between here. Different color. Really, the 4s starts here. And it gets more complicated and jumbled up the further you go. These are fine all the way up to here, except the 4s starts here, and then things start getting jumbled up. But exactly the order of all these orbitals is right here on your big cheat sheet. For now, pretend this helium, you see this notch right here? Pretend that helium is over here, and then this discussion makes a lot more sense. It's over there because it matches the properties of the noble gases. But if we put it over here and just pretend it's there for now, we can get the order of all these orbitals by using the periodic table, picturing helium over on the left. Here's an atom. I'm not going to tell you which one it is. Which atom is that? Hydrogen. Atomic number 1, so it's got 1 electron. Now pretend the helium is right here. I go, hey, okay, now what is that? You go, okay, it's atomic number 2, 2 electrons. That's helium. Now, I've done helium. Now I'm going to go down to the next period. But look what I'm doing up here. This is lithium. And the next, that's Li. And then Be is next. That's it. It's got 4. And now we skip across the gap. We get to boron. That's boron. Do you see what that next row is symbolizing? We start filling the next shell. And if I continue all the way across, that's the one on the very far right, neon. This is called the kind of a general rule, but this, the S and the P is full in the second layer. Where we're going to go when it comes to ionic compounds, or ions really, and covalent compounds, is an ionic compound has a tendency to either gain some electrons, or an ion either has gained some electrons or lost some electrons. Let's back one off of neon. Did I just do fluorine? Yeah. So that's fluorine, not neon. If it's fluorine, it's got 9 protons in its nucleus and 9 electrons. That's a neutral atom as it is. But atoms tend to have this perfect stability when you fill this octet. So fluorine has a tendency to gain an electron, thereby making it negative because that electron is negative. Looking at this tells you why fluorine tends to be a -1 ion. It doesn't form any other charge. It's either neutral or it's -1 charge. It'll never gain 2 electrons because then it'd have to stick 1 up here. It'll never lose electrons. It's never going to lose all these electrons. So that, and we would symbolize it F negative. So that's F negative, and that's F neutral. See what I'm saying? So I'm kind of introducing ions here while explaining the stable octet idea. When this was neon, it naturally had this octet full, and it was neutral. So this is telling you why the noble gases on the far right, they don't tend to form ions, so they therefore don't tend to form ionic compounds. Covalent compounds, the other compound I introduced. Covalent compounds need So fluorine can form molecules. It's got an unpaired electron. And remember, this only happens with the top right corner nonmetals. It's all nonmetals that go into molecules, that is covalent compounds. So any nonmetals that have unpaired electrons, this can form covalent bond with another atom because of it's unpaired. It basically,
Some of them.
electrons pair, but you can get a single electron from one atom and a single electron from another atom to pair with each other, and that's what holds them together. That's the covalent bond, the sharing of those two electrons. That's still skipping ahead a bit. So again, I just told you that this stable octet on neon, and all of them down that right side, this stable octet, A, they don't gain and lose electrons. They're happy how they are. And B, they don't have any unpaired electrons, so they don't form covalent bonds either. That's why the noble gases are just called noble gases. They're gases, they don't form compounds. There are some odd compounds, the larger ones will make, but we don't really run into those. In chemistry, there's always a broad rule and then a couple of weird exceptions. We don't tend to go into all the exceptions in introductory classes. So anyway, that's the stable octet. If an atom has this configuration, it's a neutral configuration. It's one of those on the far right side. If I went from neon up to argon, here's argon. The S&P is full, nothing above them. That's argon, full octet. Now the stable octet is up here. So that's why those are on the far right. Every time you get this configuration, you're on the far right in the noble gases. All right. Hydrogen and helium, that was filling here. Then across this row, that was filling here. And then once this got full, we were at neon. Now we go down again, and notice we're over here where we fill this. So these two rows over here are called the S block, because you're always filling an S orbital when you're over here. These over here are called the P blocks, because you're always filling the P orbitals over here on the right. And as you might imagine, the transition metals are where this starts. You start filling those once you get to here. But notice, we got to, where do we get? Neon, that was neon, argon. We got to argon, that's argon. Now we come down here and get to atom number 19. Argon was atom 18. Now we're filling the S block. That's your clue that you have another S orbital here before you get to the P orbitals. Do you see that? So the rest of these orders is actually encoded here in the periodic table. 1, 2, 3, 4. The fourth period, you have K and Ca, potassium and calcium. That's this. And then what you start next? The 3D. So filling across here is the 3D. And then where do you get from there? You get to here, which is going to be the 4P. So next is going to be these. And so on. You can go on and on with that. 4P, and then we drop down again here. That means the 5S is next, because we're in the S block again. Then we get back to the D block, which is now going to be 4D, 5S, this is 4D, and so on. When you get to the 7 lines, so 1, 1, 3, 1, 3, 5, okay, there's one more right here. Once you get to the 7, that's what this is down here. Right about here, you skip to a 7 orbital. I won't tend to give you those for electron configuration. I even stop at the early part of the electron configurations I mean to give you will only have maybe a couple of electrons here. We'll stop there, which means that'll be the max, somewhere right about here. Some weird things start happening when you get to the d orbitals, but I won't go into that. electronic configurations. Let me do, I'll do this. I have just an electronic